Hi everyone, and welcome back to another chemistry lesson. Today I'm going to be doing a concept from organic chemistry. So we're going to be talking about hybridization. And a lot of times you might hear your professor say things like sp3 hybridize, sp2 hybridize, sp hybridize. What does that all mean? So that's what we're going to talk about, because it's not enough to just sort of memorize this terminology. I think it's really important in OChem to really understand what is happening when things hybridize. So I'm going to start by writing out the electron configuration from the atom carbon, which might be a bit of a throwback from Gen Chem 1, but it's really important in OChem, so we're gonna write it out. So we're going to take a look at carbon on the periodic table, and we're going to see that it is in group 2, period 2, and it is 4 atoms down if we count down on period 2. Now that means that we're going to fill up our 1s2 subshell with electrons. We're also going to fill up our 2s2 subshells with electrons. And then we're going to fill up our p subshell on the level 2, just 2 electrons. We're not going to fill it up completely. We're just going to add 2 electrons there. The p can actually fit 6, so it's not full. And if we take a look at all of the electrons in level 2, that is a total of 4, and we know that carbon has 4 valence electrons, so that all checks out. Now, the thing about carbon is that it's really these 2p2 electrons that are able to bond, but we know carbon bonds 4 times, right? And the reason for that is, let's draw a little potential energy diagram here. So we got our 1s, we got our 2s, we got our 2p. We know that the s subshells have 1 orbital and the p has 3 orbitals, right? And we also know that the electrons are going to fill in one at a time. So we have 2 electrons that are available to bond in that level 2p. But what's going to happen is that all 4 of these electrons are actually going to be bonding in an sp3 hybridized molecule. Or I should say an sp3 hybridized carbon if it's bonding 4 times in a molecule. And I'll show you what I mean. So let's take a look at the molecule CH4, or methane, right? We can see that in this case carbon is bonded 4 times, and this carbon does have an sp3 hybridization. Now, what does that mean? So what's happening with an sp3 hybridization is that your 2s orbital and your 3 2p orbitals, so these 4, they're going to hybridize and form 4 orbitals that are at the same energy level. So the p is going to come down in energy level, the s is going to go up in energy level, and they're going to meet in the middle. They're going to hybridize, so they're going to just join together, and they're all going to be equal, and the electrons are going to distribute evenly in those orbitals. So now all 4 of these are available for bonding, and they're going to bond at the same energy level, which is very comfortable for the molecule. So the reason that hybridization happens is it creates a very stable molecule overall. Now, when we have an sp3 hybridized carbon, what that's saying is that 1s and 3 p's have all hybridized to create 4 sp3 orbitals. So that's telling us that we have about 25% s character and then 75% of the p character. So we know that the s is that spherical orbital and p is the dumbbell, right? And we got 3 orientations of that because we have 3 p orbitals across the xyz axes, okay? When we hybridize these 2 orbitals together, what we're going to get as a result of that is we're going to get a dumbbell shape that's like a little bit rounder. I didn't draw that very well, but basically you're going to get that p orbital shape, but a little bit rounder because it's going to have that 25% s character in it. So that's what it's going to look like. But it's still going to be pretty similar to the p. All right. So in this molecule, when we have a carbon-hydrogen bond, see if I can draw this in a different color. That's telling us that we have, so we got these sp3 hybridized orbitals here, right, on the carbon, and we have s orbitals on the hydrogens. So what's going on here is we're creating 4 sigma bonds. Okay, each one of these single bonds is a sigma bond, and the sigma bond is a result, so that sigma bond is a result of the sp3 s overlap, right? So that's what's happening in that molecule. Now, I want to talk a little bit about double bonds and triple bonds because I think that it starts to make a little bit more sense when we understand what is happening with the hybridization. So let me clear up some space here so that we can talk about this. All right. And I'm going to erase that molecule. We're going to draw a different molecule. Okay. So let me erase this too. Okay. Let's say that we have an sp2 hybridization. So I'm going to use a double bonded carbon as an example here. And we know if we have a double bond, let's say it's just the 2 carbons, that means that we have 2 hydrogens on either side because that carbon, once it's in a double bond, can't fit 3 hydrogens anymore. It's going to have 2. So let's say we have this molecule right here. The hybridization on both of these carbons is no longer sp3, it's now sp2. Okay? And the reason for that is, again, if we're always going to have these 4 orbitals, right? The orbitals are still there. If we're hybridizing only 2 of the p orbitals, so this is going to be sp2, so we're hybridizing 1s and 2 p orbitals, we have an available p orbital. Available p orbital. This is really important if you want to form a double bond, because in order to have a double bond, you have to have an available p orbital on the carbon, on both of the carbons. And that interaction between those p orbitals on each carbon, that's your pi bond. Right? So we know in a double bond, we got 1 sigma bond. So we have 1 sigma bond and 1 pi bond. That's what a double bond is. And that can't exist, that pi bond can't exist if we're sp3 hybridized, right? sp3 implies that we have no p orbitals, so we cannot have a pi bond there. So just keep that in mind. If we're talking about sp3, we're talking about single bonds. All right, so again, in this case, the sigma bond is a result of an sp2 overlap between those 2 carbons. So we have sp2 overlap. And the pi bond is going to be that pp overlap, right? So that's what's actually creating those bonds. Both of these carbons are sp2 hybridized. Okay, now real quick before we wrap up, I want to talk about a triple bond, right? So let me just adjust this picture right here. So I'm gonna make this a triple bond, and we know if that's a triple bond, we can't have 4 hydrogens. We can only have 1 on each side. Okay, we're not sp2 hybridized anymore. Now we're sp hybridized, right? We're sp hybridized. So that's telling us that we have 2 available p orbitals now, which is, again, important because now we're going to have 2 pi bonds instead of the 1. So what's going to happen is we're going to have sort of another p orbital interaction to create that second pi bond. And now what we have is we have 1 sigma bond due to the sp-sp overlap between those carbons. And then we have 2 pi bonds, and that's because we have p and p overlap, but we have 2 of those happening. So we have like 2 available p orbitals on each carbon. So it's a total of 4 p orbitals, but it's 2 pi bonds because those 2 orbitals are going to be interacting, right? And that's going to be the 2 separate pi bonds. So hopefully that makes a little bit more sense in terms of what these hybridization letters and numbers actually mean. Let me know if you have any questions. You can leave them in the comments and I will answer. Thanks, y'all.